Welcome to Lesson 1, the Angle Bisector Theorem. I actually have a little example to explain the angle bisector theorem. This is a soccer field, and we've got a player that is trying to score a goal, and we have the goalie here who's trying to defend the goal. Now, I don't know if you've noticed, but a goalie never really just stands right in the center of the goal. They sometimes come out a little bit, but still wouldn't really stand in the center of the goal. Because can you see how then the kicker would have so much wider of a shot on this side than on the other side? So the question is, where does the goalie naturally stand? Well, the goalie's going to want to stand maybe here-ish. And the reason for that is because then the distance on this side and the distance on this side would be more equal. And so the goalie has the best chance of being able to go either way to defend the goal. Now, of course, the goalie could play further out or further in. That's based on strategy and preference. But the idea is as long as the goalie is standing somewhere on this line, they're going to have the best chance of being able to defend. And that line is special because it is the bisector of that angle. The angle bisector. So cutting these into two congruent parts, that happens to be the line where the goalie has the best chance of defending on either side. So lesson 1, the angle bisector theorem, says just that if you have a point that's on that angle bisector, you can tell it's an angle bisector from the swoop, then if we measure straight to each side of the angle, it is equidistant to those two sides of the angle. This point is equidistant. And it turns out that the converse is also true. If you were to find a point that was nice and equally spaced from each side of that angle, then it's guaranteed that that point you found is on the angle bisector. That's the converse of the angle bisector theorem. So we've got 6 problems down here using those theorems, and we're going to do the first 2 together. The first one says to find the measure of angle WYZ. That's that lower angle down there. Now it seems like that lower angle must also be 28 degrees, but how do we know that for sure? How do we know that this is an angle bisector? Well, I can see that point W is equidistant to X and to Z. That's reminding me of this converse, right? I have a point that's equidistant, so then I can say that that is an angle bisector. So I can say that the measure of angle WYZ is 28 degrees. Now for each of these, we're also going to write whether we use the angle bisector theorem or the converse. And like I said, we were given that equidistant to the sides, and we concluded that we must be on that angle bisector, so we used the converse. And just underline what theorem you've chosen. So you remember that you'll have a box around your answer and an underline on which theorem you used. Example number 2. This time I see a point, and I know it's on the angle bisector because I can see those two swoops, right? So I am starting with a point that is on the angle bisector for sure. Now the information that's going to be useful to me will be this conclusion that this little chunk and that little chunk are congruent. Algebraically, that would mean that 4x minus 1 is equal to 3x plus 2, and then I'm just going to solve that. And I find out that x equals 3. Now be careful because it is actually asking us to find the length of segment QS, and that's the 4x minus 1 piece. So we'll want to plug in that x equals 3. 4 times 3 minus 1 is 11. It wouldn't hurt to check the other segment too. 3 times 3 plus 2 is 11, because that's what we were looking for, is both of those would be equidistant. And because on this one, the given was that we were on the angle bisector, I saw those swoops already marked, I used the angle bisector theorem for this one. So now I'd like you to finish the other 4 problems. Make sure that you give me the answer and you tell me which theorem you used, the angle bisector theorem or the converse.